Saturday Morning Physics is sponsored by the University of Michigan Department of Physics and by gifts from friends of the program. Local broadcast is made possible by Pfizer Incorporated.
Today's lecture is the first of two on the subject of gravitational wave astronomy. Today I want to tell you what gravitational waves are, where they come from, and why they are so incredibly difficult to detect. Now next week, in the second lecture, I'll tell you why we think we can catch them anyway. I'll describe different types of detectors that have been built and are now operational that are looking for gravitational waves. I'll talk in particular about this one project that Tim mentioned called LIGO, which stands for Laser Interferometric Gravitational Wave Observatory, project that I'm involved in. And I'll discuss some of the results of searches that we've carried out looking for gravitational waves and discuss the future prospects for discovery. Okay, before we talk about gravitational waves though, I'd like to remind you of the basic properties of waves. I want to go through a refresher on wave motion. Loosely speaking, waves are oscillating disturbances that propagate, and a classic example would be ripples on a pond. These ripples propagate out to the edges of the pond. They may reflect off the edges of the pond. And on a larger scale, we have ocean waves. These disturbances can propagate very long distances across the Pacific Ocean, for example. Typically, waves have excursions that are either positive or negative, not always, but typically that's the case. And in this case, the excursions that describe this wave motion are displacements of water from nominal position. There are other examples, of course, in nature, and ones that we can fabricate. We have the water waves I just showed you pictures of. If you pluck a guitar string, you can see a certain fuzziness, in that guitar string, which is a wave. It happens to be what's known as a standing wave, but it's still a wave, and it's quite intuitive if you look at it. Now here's another example where I have a rope, which I'm pulling somewhat tautly, and if I now jerk it, you can see the wave travel back and forth along the length of the rope. If I pull hard, the wave moves quickly. If I relax the tension, the wave moves more slowly. The wave speed depends on the tension in the rope. Okay, so those are two fairly intuitive examples of wave motion. Let me talk about something that's a little bit less intuitive, but still something you can probably understand reasonably well. If you imagine seismic waves after an earthquake. I don't know how many of you have ever been in an earthquake. I've been in a few when I lived in California. And it's very easy to imagine that as being a wave phenomenon. You feel yourself swaying back and forth as the seismic wave passes underneath you. You don't normally see the ground rippling, literally, at least you don't want to be in that kind of earthquake. But there is wave motion in action there. Another example are sound waves. When I'm talking to you, I'm sending out pressure waves through the air molecules in this room that are reaching you at roughly 800 miles per hour because that's the speed that molecules move at. I'm emitting pressure waves at you that carries the information in sound. Now, somewhat less intuitive, more abstract, would be electromagnetic waves, namely light. These are oscillating electric and magnetic fields, which I'll talk about a bit more in a moment, but they're somewhat abstract. You can't see an electric field directly. And finally, we have gravitational waves, which are even more abstract. These are oscillations of space itself, and I'll talk more about that shortly. But first, let me talk a little bit more about how we characterize waves. We have longitudinal waves and transverse waves. Waves are longitudinal if the oscillation in question is along the direction of motion. If I have a slinky, like this, and I give it a really hard push, I can destroy my microphone. Let's see. Watch the pulse that's created when I push. That's a longitudinal wave. The oscillations of the rings are along the direction, or opposite direction of the propagation of the wave. Okay. Sound waves, of course, are also another form of longitudinal oscillation. As I speak to you, the air molecules are vibrating back and forth along the direction between me and you. I can also do this to my slinky. I can wave it from side to side. That's creating a different kind of wave. That's called a transverse wave. The oscillation is perpendicular to the direction of motion. What other waves are transverse? The pulse that I created on that rope was an example of a transverse wave. Let me show you another one that's not quite as familiar to you. This is known as a Jacob's ladder. It actually allows me to produce torsion waves. So if I take the bottom one of these rungs and I give it a hard twist, there's a torsion wave that travels to the top of the Jacob's ladder and comes right back down to me. Okay? That's also a transverse wave. These rungs are oscillating this way, transverse, perpendicular to the direction of propagation of the wave. Okay. Electromagnetic waves are also transverse, and let me talk about that. An electromagnetic wave is essentially a bundle of electric and magnetic fields that are oscillating like mad as they self-generate, self-propagate through space. In particular, here we have a picture from one of our elementary textbooks of an electromagnetic wave. It shows an electric field oscillating up and down in this plane, and a magnetic field oscillating this way in the horizontal plane. The direction of propagation of the wave is from left to right. So these are clearly transverse oscillations. The oscillations are perpendicular to the direction of motion. Now I can actually turn this whole pattern 90 degrees. I can rotate it around the axis that defines the propagation direction so that my electric field is horizontal and my magnetic field is perpendicular. That's a different polarization, but still a transverse wave. And electromagnetic waves have two independent polarizations. Of course, they travel at the speed of light, because they are light, and nothing moves faster, including gravitational waves. What about surface water waves? Just as a momentary digression, what do you think? Are surface water waves, like these ocean waves, are they transverse or longitudinal? We don't have a consensus. And there's a good reason for that. They're both. Ocean waves, water waves in general, surface water waves, are indeed both transverse and longitudinal. These water molecules, if you're in deep water, the water molecules undergo circular motion as a wave passes. And if you've played in the surf, if you've done any body surfing or board surfing, oops, let me go back for a moment, you're probably familiar with the fact that not only do the waves pick you up and let you down again, that's the transverse motion as the wave propagates toward the beach, they also pull you toward them as they approach you, and then they also carry you with them as they pass you. So it's both longitudinal and transverse motion there. Another characteristic of waves are wavelength and frequency. In particular, if we have idealized sinusoidal waves, as indicated in this picture here, then we have a very well-defined wavelength. Imagine taking a snapshot of a wave that passes you, say a snapshot of a wave on a string, for example, and just measuring the distance from one crest of a sinusoidal wave to the next crest. We call that the wavelength. The period is the time between successive crests if you sit and watch the wave pass by you. You just measure, I had a crest here, I wait some certain amount of time, I get another crest. That difference in time is the period. The frequency is simply the period 1 over the period. It's the number of crests that pass you per unit time. And the speed is, of course, the wavelength divided by the period. Because if you imagine a wave passing by you, if it has a certain distance between the crests, and it takes a certain amount of time for one crest to pass you and then the next crest to pass you, then the speed must be the wavelength divided by the period. We also write it as a wavelength times the frequency. Okay, let me talk about sound waves. Audible sound waves have frequencies in the range of 20 hertz to 20 kilohertz. Now, as we get older, we typically lose some of our hearing at higher frequencies, so this upper limit may depend on your age. It may also depend on what sort of music you listen to as a teenager. Now, at room temperature, the speed of sound in air is about 340 meters per second. It's almost 800 miles per hour. And let me play some examples of audio clips for you. This is 60 hertz, which has a wavelength of 19 feet in the air. Oops. I think it'll work. Okay, that may be a very familiar sound to you. If you've ever had a lousy stereo like the ones I've had, then if you have poor grounding in your stereo, you're familiar with that hum. Okay, that's a 60 hertz hum that comes from the electric fields in your house, from the wall sockets. Now let's play a higher frequency. This is 440 hertz. That corresponds roughly to middle A. But it doesn't sound much like an instrument, does it? A musical instrument. I'll come back to that in a moment. This is a higher frequency, 1,000 hertz. This is 4 kilohertz. Not all of you may be able to hear that. And I'm curious to know how many of you can hear this. Raise your hand if you can hear that. I'll play it one more time to give you another chance. Okay, so it truly is an upper limit on the audible range of human beings. We don't have any dogs in the audience, so we can't ask them. Okay. Let me talk about the electromagnetic spectrum. We've talked about wavelength and frequency of sound waves. We also have the same characteristics for electromagnetic waves, for light. This gray bar here, or was gray on my computer, it looks a little bit different color here, shows frequency along the top here, wavelength along the top in meters, and along the bottom we have frequency in hertz. In the middle, roughly, we have the visible spectrum, and we see colors that have been magnified here. If you look along to the left, you see infrared radiation that corresponds to longer wavelengths, lower frequencies. We get into the radio waves at still lower frequencies, and very long radio waves at very low frequencies. If we go in the other direction from visible, we have ultraviolet at higher frequencies. You can't see that, of course, but you can feel it if you get sunburn. We have X-rays at still higher frequencies, and at the highest frequencies, we have gamma rays. If you break up the radio wave spectrum, there are some interesting points, like AM radio here at 1 megahertz roughly, and FM radio at about 100 megahertz, and agrees to what you see on the dials on your own radios. Okay, so far I've really been talking in terms of idealized sinusoidal waves, where we have a one well-defined wavelength and a corresponding well-defined frequency. But many waves are not that way. They actually have a broad spectrum of different frequencies, different wavelengths that they're made up of. And for example, if we talk about audio waves, sound waves, we have human speech, which can be quite complicated, automobile engines, the chirps of birds, and even instrumental notes contain a rich spectrum of frequencies. Let me play for you a piano note, again at the same 440 hertz, the middle A that I played for you earlier. Now, it's not a particularly good piano. It's the one I have at home, which is a cheap electronic piano, but it sounds roughly like a piano. And if we look at this spectrum that it produces, it looks like this. We have, indeed, a lot of energy, so to speak, at 440 hertz, what is nominally middle A. But there's even more energy here at 880 hertz, twice the frequency of 440. Let me play a different musical note for you. Again, this is a cheap rendition of a pipe organ. And clearly, it's not a high-fidelity recording. But if we look at the spectrum of that, it has some similarities. It again has a strong line at 440 hertz, but in fact it's stronger, relatively speaking, than the one at 880. And we have some additional frequencies up here at the third and fourth harmonics of the fundamental. Okay. Let me play for you a sample of human speech. Okay. So that's the spectrum produced by a middle-aged man. I thought about saying young man, but I figured I couldn't get away with it, so I left it. So this is a spectrum that shows you the frequency content of that recording I just played for you. Now let's listen to the same words spoken by someone else. Okay, a higher pitch. Okay, those are my daughters, Lizzie and Katie, who are 6 years old. And you can see that the spectra looks similar qualitatively to what I have over here, and they should look similar. These are the same two words that are being spoken, but the pitch is higher. They have higher frequencies because they have smaller voice boxes than I have. Okay, now, as it turns out, and we'll discuss this in more detail a bit later, gravitational waves are expected to arrive with a variety of spectral characteristics. We may have things that look like pure sinusoids, but we also have very broad band disturbances that are more like the speech that we project ourselves. Now, as it happens, the waves that we think we can detect here on the Earth's surface tend to be in the audible band. I'll talk more about that in detail next week. Now, the gravitational wave speed is actually very, very high compared to the sound speed. So although we have comparable frequencies, the wavelengths are very different. The wavelengths are almost 1 million times longer for gravitational waves at the same frequency than they are for sound waves. So for 100 hertz, sound and air produces a wavelength of about 11 feet. But for a gravitational wave, the wavelength would be almost 2,000 miles. That's just a difference in the speeds of sound waves and gravitational waves. Now, waves are also characterized by interference, either with themselves or with other waves. This is an example of two interfering ripples on a pond. You can see there's an interesting pattern here where the two ripples come together. In some cases, the crest of one wave overlaps with the crest of another wave, and they pile on top of each other, making a still higher wave. In other places, the crest of one overlaps with the trough of another, creating destructive interference. Here's a different way to look at it. Imagine that you have two waves synchronized such that their crests are on top of each other, so the two top waves add together to form the bigger wave, which has twice the amplitude, twice the strength of either of the upper waves alone. If we shift one of these waves relative to the other, so that now that the crest no longer overlaps exactly with the crest of the other wave, we still get partial constructive interference. This wave is a little higher than either one of these alone, but it's not twice as high. And finally, if we move one wave a full half cycle with respect to the other wave, we get complete cancellation, and that's known as destructive interference. We have a demonstration of that with sound waves. What I'm going to do is turn on two speakers that are being driven by the same oscillator at about 2.5 kilohertz, and you'll be able to hear the sound quite easily. And what I'd like you to do is plug up one ear and move your head around, and you should be able to sense changes in the intensity of these waves. If you're lucky, you might even find a point where you get complete destructive interference. So that's a wave pattern that we can set up here in this room. It pervades the entire room when those two speakers are running. Okay. Now, what about gravitational waves? I've talked about a lot of other waves. Let's talk now about gravitational waves. Recall that a wave is a disturbance of some kind that propagates. So what exactly is being disturbed by a gravitational wave? Well, it's space itself. Okay. Now, before we discuss how such a disturbance can propagate, we first need to understand how can space be disturbed by anything. We don't normally think of space as being disturbed. Things sit in space, but they don't disturb it. But in fact, they do disturb it. Einstein was the first person to realize this almost 100 years ago, and he wrote down what are known as the Einstein field equations. This single equation really represents 16 equations, 10 of which are independent of each other. I don't want to get into the mathematics of what this equation means, but qualitatively, it's telling us that the curvature of space, and I'll illustrate that in a moment, which is embodied in the left-hand side of the equation, is related to the energy and momentum of matter and other fields embodied in the right-hand side of the equation, what we call T. Now, unfortunately, except for a handful of very special problems with lots of symmetry, for example, spherical symmetry, these equations must be solved numerically. They cannot be solved algebraically. And even solving them numerically is quite difficult. It's a challenge for our highest speed computers. But the essence of these equations can actually be understood in a qualitative way. John Wheeler, who was a general relativity pioneer, said it in a nice way. He says that matter tells space-time how to curve, and curved space tells matter how to move. So let me illustrate that graphically. Let's imagine we have a rubber sheet model of space. If we have a very heavy object sitting in space, it deforms space. It curves it. And if we place another mass, like this little green ball, in the vicinity of that curvature, it rolls into the depression that is formed by this very heavy mass. And in fact, if we put another heavy object in place, it would deepen that depression. So they'd both be contributing to the same depression. And what arises from that are what are known as highly nonlinear equations. Now, we have an illustration of that over here. We have a rubber sheet that Warren and Mark have set up for us. And I have a steel ball I'm going to place in the center of this rubber sheet. There's a certain amount of oscillation right there. So this heavy ball is weighing down the rubber sheet, and if I place another small object, this might represent a supermassive black hole, for example, at the center of our galaxy, and I place an ordinary star in its vicinity, it's going to be attracted toward the ball simply because it's rolling into this depression. Now, this is a two-dimensional analog of what's really happening in three-dimensional space, but our human minds are not able really to comprehend or to picture what's happening in 3 dimensions. Just for fun, let me throw some more marbles in there, more stars, and show you what happens when a major black hole comes in the vicinity of lots of little stars. So there's an apparent attraction here. There's really no literal attraction between the marbles and the ball. It's only an apparent attraction caused by the fact that they're both sitting in this deformed surface. And the three-dimensional analog of that is what's happening in general relativity. That's what's embodied in Einstein's equations. In fact, let me show you another example that's a little bit more pertinent to what I'll be discussing a bit later. Here we have two equal mass objects that are in a common depression, and they appear to orbit each other, but in fact they're just both rolling in the same depression formed by space. Now, in this case, the depression was created by the curvature of the glass, but in general relativity, the depression would be created by the presence of the balls themselves. Okay, now let's imagine we have two very compact stars, for example, black holes or neutron stars, that are orbiting each other very rapidly. They're very close into each other. They are going to swirl space. They're going to create ripples in space that will propagate just like those ripples on a pond will propagate. And if we're lucky, those ripples will propagate to our part of the universe so that we can detect them. And if we're lucky, those waves will be strong enough that we can detect them. Now you might ask, are there really such things out there, or is this just science fiction? Well, the answer is yes. We do know of such star systems. In 1974, Joe Taylor and Russell Hulse discovered a binary system that has two neutron stars, one of which is a pulsar. Here's a diagram of that system. It shows one pulsar, which has a frequency of 17 hertz. I'll discuss pulsars in a moment. And it's in orbit with an unseen neutron star whose presence we infer from studying the behavior of the neutron star that we can see. So let me digress for a few moments on pulsars. This system has an orbital period of almost 8 hours. Under a variety of conditions, a star can become so massive that it can no longer support itself. The atomic forces that hold a star up can no longer support it. And its core undergoes collapse. And essentially what happens are protons combine with electrons to form neutrons, emitting neutrinos in that process. In fact, you heard a lecture on neutrinos just a few weeks ago. These escaping neutrinos then explode the outer shell, the envelope of our star, creating what's called a supernova, a very bright thing that one can see in the invisible and in other frequencies. Now, the core that's left behind is like a gigantic atomic nucleus with a density that is simply stupendous. Imagine taking all of the sun and sticking it into Ann Arbor, compressing it down to that kind of density. Numerically, you end up with densities of order 10 to the 14 grams per cubic centimeter. So if you had a teaspoonful of this stuff, it would weigh 1 billion tons. Okay. Now, that shrunken core cannot lose its angular momentum. We have to conserve angular momentum, the amount of rotational motion. And so you can imagine what happens if you have a slowly rotating star core, like so, and you suddenly compress it, then there's a speed up in its rotation. That's just conservation of angular momentum. It's the same effect that causes ice skaters who go into a pirouette to speed up as they bring their arms in. As they reduce the moment of inertia, the rotational velocity has to compensate to conserve the total angular momentum. Okay, so that's the sort of process that happens in these supernova compressions when the core of a star collapses. And as a result, there are magnetic fields that are very intense that are created in that process. And that leads to the final neutron star having strong magnetic north and south poles, similar to what we have here on Earth, but magnified by many orders of magnitude. And just like we have charged particles here on the Earth that oscillate back and forth between the north and south magnetic poles, creating what we call the northern lights or the aurora, we have the same sort of phenomenon on a neutron star, but with a much higher intensity. That creates hot spots of radiation at the poles of the neutron star, the magnetic poles of a neutron star, as indicated here. So you have a hot spot here and a hot spot there. And if those magnetic poles are not aligned with the rotation axis of the star, just like we have here on the Earth, our north magnetic pole is not at the north pole of the Earth, then you have a radiation beam that comes off of each of these poles that sweeps around the sky like a lighthouse beacon as the star rotates. And some of these stars rotate very fast, the most extreme case being 640 hertz. So let me illustrate that. This is a mock-up of a neutron star using an ordinary globe into which Warren and Mark have stuffed a light bulb. And as I rotate the globe, you'll see a little flash as you see the hot spot that corresponds to what's happening on the neutron star. Not sure everyone can see that. Okay. So that's the sort of thing that you can see if you look at a pulsar, except that you're looking typically at different frequencies. No, let's turn that back off. Okay. Now, most known pulsars were first seen, and many are still seen, in radio waves, but some of them also emit X-rays. This is a picture taken showing the X-ray emission of the Crab pulsar, which is buried inside of that Crab nebula. Keep losing my pointer. Oh, here it is. So this is what it looks like when the lighthouse beacon points at us. We see X-rays coming out of the pulsar buried inside of this nebula, and when the lighthouse beacon goes around to a different direction, we can no longer see it. This pulsar came from a supernova that happened about 1,000 years ago and was observed by Chinese astronomers at that time. Now, because a neutron star is so massive and spinning so fast, it behaves very much like a flywheel, like the flywheel on a car. It's extremely stable in its rotation. And since we have this lighthouse beacon that's swinging around according to that rotational frequency, we get very periodic radio or X-ray pulses from the pulsar, hence its name. Now, some pulsars are in fact more stable than some of our best atomic clocks here on the Earth. That allows us to make very precise measurements of their properties, and if they happen to be in a binary system, we can measure indirectly the parameters of that binary system. Let's go back to this Taylor-Halsey system. As I said, it has one pulsar that's orbiting an unseen companion star. By measuring all the pulses that we see on a very regular basis, but at a slightly modulated basis, we can infer the dynamics of this orbit quite precisely. This shows you the present orbital extent of that binary system. It has a period of 8 hours. For comparison, here's the diameter of the Sun. As it turns out, if you look very closely at that orbital set of parameters, we infer that the orbit is slowly shrinking. 250 million years from now, it's going to be almost 3 times smaller than it is right now. As it turns out, that process accelerates, and it only takes another 50 million years for this orbit to go all the way down to 0, in which case the 2 neutron stars collide rather dramatically. This orbit is shrinking about 3 millimeters every revolution, that is every 8 hours. So we expect coalescence of the system in about 300 million years. So the natural question is, why is this orbit decaying? Yeah, it's emitting gravitational waves. It's losing energy to gravitational waves. Okay, just like a satellite orbiting the Earth. In that case, a satellite may hit molecules in space. It's not a pure vacuum out there, and it slows down as it speeds up. It's an interesting phenomenon. As it loses energy, it comes closer to the Earth. The same thing happens for this binary system. So why are we so sure that we understand the decay of this binary system? Maybe we're making too big of a jump. Well, we can measure very precisely these pulsar signals and can infer the orbital parameters. Einstein tells us how to interpret that. His theory of general relativity predicts, absolutely, no fudge factors, what the gravitational radiation energy loss should be. And of course, the question is, did he get it right? Well, Einstein usually does get things right, and this shows you a comparison between his prediction and the actual data. The smooth curve shows you the prediction from general relativity, no fudge factors, no free parameters, just the absolute prediction based on what we can measure at any moment in time from that orbital system, and the dots are the measured data. So it's just beautiful agreement. Now, the next question is, can we detect those waves? Clearly the system is emitting gravitational waves. Can we see those waves here on the Earth? Well, unfortunately, no, we cannot. For reasons that we'll talk about in detail next week, we cannot see gravitational waves here on the Earth's surface that have a frequency much lower than about 10 hertz. In fact, it's a few tens of hertz right at the moment. And this system has a characteristic frequency that is 70 microhertz because it has an orbital period of 8 hours. Okay, so what if we waited? If we wait 300 million years, what would we see? Well, we would see, or in some sense hear, a chirp. This illustrates that basic idea. On the right-hand side, I have 4 graphs that show you the waveform of a gravitational wave, the oscillations of space, for 4 1-second intervals near the end of this inspiraling process that will take 300 million years. This is with 1 day left to go in the death spiral of the system. You can see that the frequency is about 2 hertz, or 2 crests of this wave in this 1-second period with 1 day left to go. When there's 1 hour left to go, the frequency is increased to about 6 hertz, if you count those crests. If you go down to 1 minute left to go in the system, we're up to 24 hertz. And finally, the very last second of its life, it looks like this. It goes up into the kilohertz range. It's a very dramatic chirp in that last second. It's analogous to a little mechanical demo we have here, where I have a golf ball that I'm going to rotate around a glass bowl that's conically shaped. Oh, that's it. Yes, there you go. Mark's got the. Thanks. Let me do that for you again. So there's a lot of dissipation, in this case due to friction. In the case of the neutron stars, it's due to gravitational wave emission. And you'll notice that the frequency increases as the ball gets closer and closer. So that's a poor man's version of a gravitational wave chirp. Okay. Now let me play for you something that's a little bit closer to what actually happens. So here's an audio clip where I've taken one of these gravitational wave predictions, just run it through a digitizer. Okay, that's what we'd love to hear in one of our detectors. Let me play that for you one more time. You hear you hear the hum, and then it slowly gets higher and higher in its frequency. Okay, that would be lovely to hear in our detectors. We haven't heard it yet, but we're listening. Okay, and let me talk about how waves actually propagate. What are gravitational waves, after all? Well, we say that they're ripples in space-time fabric. Their perturbations propagate in a way that's very similar to that of light. They move the same speed of light. Another way of saying that is that the graviton and the photon are both massless. They have two independent polarizations, and to understand that, let me draw a diagram for you. Imagine that we have a ring of test masses just floating out in space. Imagine you have a bunch of marbles, for example, that are strung as beads very loosely. And we just have them floating out in space, and a gravitational wave hits this ring normal to the plane of the ring itself. What's going to happen is that part of the time, for half of the wave, space itself is going to stretch between those marbles vertically, and it's going to compress horizontally this way. This is what's known as a quadrupolar pattern of oscillation. And when I say that space is stretching, I mean that if I were to measure this by shining light from one marble to the next marble and measuring how long it takes to go there and back again, I would find a difference when this wave is passing me. Now, half a cycle later, I would see the reverse. I would see space stretching this way horizontally and compressing vertically. So that's one of the polarizations that describe a gravitational wave oscillation. This is space itself oscillating in this way. And if I rotate that pattern 45 degrees, I get the other independent polarization. So it's very much like light, except that instead of rotating the pattern 90 degrees, I rotate it 45 degrees. Now, how do we describe the strength of a gravitational wave? Well, the most natural way to do it is in terms of fractional change in distance, that is, strain. We denote that strain by the quantity h. It's a dimensionless quantity, and it refers to the displacement of space from its nominal position. If you have an object that has a nominal length of L and it gets stretched or compressed by a certain delta L, then h is a ratio of those two. If you're trying to measure h, if you're a scientist trying to measure what h is, and you have a fixed precision on delta L, it pays you to have a very large L, a very large lever arm with which to measure h itself. And in our case, in the LIGO project, L is 4 kilometers. Here's a graduate student's depiction of oscillating space. It shows you space stretching and compressing, alternating in the two dimensions. This is the change in the length, delta L, and this is the nominal length between the two. In this case, the amount of strain oscillation has been magnified by about 20 orders of magnitude. We wish it were that easy to detect. Okay, now I'm going to talk about how we're going to look for gravitational waves from outer space, but you might ask, why don't we just generate them? Why do we have to rely on what nature sends us? Why don't we just make some gravitational waves and detect them? And there is a precedent for that. Back in the 19th century, after James Clerk Maxwell showed us that electric and magnetic fields are unified in the sense that if you add one term to one of the existing equations at that time, you end up with what are known as the 4 Maxwell equations, and those equations directly predict the propagation of electromagnetic fields, as I showed you schematically earlier. And Heinrich Hertz wanted to test that. So he set up a contraption that allowed him to generate electromagnetic waves. This is a simplified, oops, I should not point at my laptop, excuse me. That was pretty stupid. Okay, so if you set up an electronic circuit that resonates, you can drive electrons up and down in this transmitting antenna, and those electrons create electric fields that are also oscillating at the same frequency, and that creates a wave that then propagates off, and ideally you'd like to detect that with your detector. So let me illustrate that idea. Here we have one of these electromagnetic oscillators. It's similar to what's drawn on the diagram up there. There's a transmitting antenna here that is forcing electrons to go back and forth at a frequency that's fairly high. And now I have a receiving antenna, my Hertz detector, that is simply a passive pair of antennae that are connected to a light bulb. And so this light bulb is sensing, indirectly, the electromagnetic wave created by this transmitting antenna. Electrons are being forced to go back and forth in this antenna, and they make the light bulb light up. Because this is detection of a gravitational wave. This is essentially what Hertz did back in the 19th century to show that Maxwell's equations were indeed correct, and his prediction that light was made of electromagnetic waves was correct. So why don't we do the same thing for gravitational waves? Well, we'd like to, but can we swirl space hard enough and fast enough to make a detectable gravitational wave? Well, let's look at some of the numbers. First, let's look at the formula that describes this process. I don't want to go through it in detail, but basically the strain level, h, is proportional to some constants, Newton's constant g, speed of light to the 4th power in the bottom, the distance, 1 over the distance between us and the source of gravitational waves, and what's known as a second time derivative of a quadrupole moment. Now, I don't want to get into the details of what a quadrupole moment is, but roughly it's proportional to the mass of an object times its radius squared. Okay. Let's plug in some numbers. So if we plug in Newton's gravitational constant, the speed of light, we find that this constant g over c to the 4th is about 8 times 10 to the minus 45 in our ordinary units of meters, seconds, and kilograms. It's a pretty small number. What about the rest of that equation? Well, we have 1 over r here, and we have the second time derivative. Now, if we're going to detect gravitational waves, we need to understand what the wavelength is. So let's think about a particular problem. Imagine that we have 1 meter weights, 1 ton weights that are suspended on a steel bar that has a 1 meter radius. And imagine that we take that dumbbell and rotate it at a kilohertz, 60,000 RPM. So that ought to swirl some space, right? I mean, that ought to do it. Well, let's plug in the numbers. If you pretend, first of all, that the steel rod is not going to tear apart, which it would, let's pretend that it doesn't, could we plausibly generate gravitational waves? Well, for a 1 kilohertz rotation, that time derivative I just showed you is equivalent to 4 pi squared times 1,000 hertz squared. And the wavelength of the radiation that would be generated would be about 150 kilometers. Now, if you want to establish that you're measuring gravitational waves and not just measuring gravitational forces that happen to be close to where you're measuring, you need to be several wavelengths away from your source. So that means we need to make r at least 500 kilometers to verify that we are seeing actual radiation. So if we now plug in the numbers, we get a ballpark strain estimate from this contraption of 10 to the minus 44. Okay, so we're not going to be able to do what Hertz did. We cannot generate our own gravitational waves and then measure them. We have to rely on what nature sends us. So what does nature send us? Okay. Let's return to our astrophysical dumbbell of 2 neutron stars that are not attached by a steel rod, but are in some sense attached by their gravitational attraction to each other. Or in general relativity terms, we say they're both stuck in the same depression that they've jointly made together. So let's imagine 2 neutron stars. Each has a mass of 1.4 solar masses. That's the nominal mass we expect for neutron stars. They're in a circular orbit of radius 20 kilometers, so they're just about to collide. They're at the very end of that in-spiral I talked about earlier. The resulting orbital frequency is 400 hertz. So you have 2 stars heavier than the sun orbiting each other at 400 hertz. It's a violent process. And the resulting gravitational wave frequency is 800 hertz. This is another graduate student depiction. Actually, it's a postdoc depiction of the process. If we plug our numbers into our formula, we find that now the strain is a whopping 10 to the minus 21. So it's 23 orders of magnitude bigger than what I showed you earlier if the distance between us and our source is 15 megaparsecs. Now, 50 megaparsecs is about 50 million light years, and that happens to be the distance between us and the center of the Virgo cluster, which has lots of galaxies with lots of stars that might do this sort of thing. 10 to the minus 21 happens to be the sensitivity that modern gravitational wave detectors have. I'll talk about that in detail next week. How small is 10 to the minus 21 anyway? Well, that's one way to write it. Another way is 1 over a million cubed divided by another factor of 1,000. Or the diameter of an atom divided by the distance between the Earth and the Sun. So it is an experimental challenge to measure something like that. And I'll tell you about it next week. Okay, now how often does this sort of thing happen? How often do we have these coalescences of neutron stars with other neutron stars, at least in our vicinity of the universe, where the waves that are produced might be strong enough for us to detect them? Well, we don't know. There are estimates. Their estimates are based on 2 different methods. One is to use the number of neutron star binaries in our own galaxy, of which we have a grand total of 3. So we have low statistics. Or one can do an a priori calculation based on what we know about stellar evolution and binary system evolution and figure out how often would 2 stars both go supernova, creating neutron stars, without flinging each other apart. Okay, and that's a tricky calculation, as you might imagine. There are large uncertainties. Our best estimates are that if you can see out to, say, 20 megaparsecs, then, which is about 65 million light years, then the frequency at which this happens is something like 1 in 70 years up to 1 in 4 years. Okay. So the present instruments, which have about this sensitivity, need some good luck if we're going to see anything in the next few years. But as I'll discuss next week, very modest improvements in our detectors will allow us to ensure detection. That's not obvious, but I'll explain it next week. Now, what else might we see besides these two neutron star processes? We could have other binary compact star systems. We could have a neutron star orbiting a black hole, or even a black hole orbiting another black hole. And again, the estimates have very large uncertainties, but some of the estimates are actually comparable to those for neutron star systems. And that's good because black holes are generally heavier than neutron stars. That means that when they're swirling around each other, they swirl space more strongly. And so we get stronger waves, and that means that we can see these things farther out. So the observable event rate should be higher for these if we have the same rate per galaxy. Something else we might see is a supernova. This is a numerical relativity calculation of what it looks like inside of a supernova. This is the core of the star here. And it's a very violent process. As long as it's not completely spherically symmetric, we do expect a certain amount of asymmetry that leads to gravitational wave production. If it's purely spherically symmetric, then we don't get gravitational wave. That's one of the oddities of general relativity. But if we have this kind of asymmetry, there's a good chance we will see something. Let me play for you what that would sound like. So hold on to your hats. That's it. That's what we've got to catch with our detectors. Okay, it's not nearly as nice as that chirp I played for you earlier. We have to be really careful if we're going to claim we've heard something like that from gravitational waves. And I'll explain how we think we can be that careful next week. Okay, another potential source would be a cosmic gravitational wave background, a remnant from the Big Bang. You probably know quite a bit about the fluctuations of the cosmic microwave radiation background that was discussed in a couple of lectures earlier in the semester. These are fluctuations in that pervasive background of 3-degree Kelvin radiation that comes at us from all directions. Those fluctuations tell us a great deal about what happened in the Big Bang and what has happened since the Big Bang. And we would like to see something like that in gravitational waves. But unfortunately, it's unlikely that we will. The so-called standard model of cosmology predicts that this will be too small to be detectable at the frequencies that we're looking at here on the Earth. But I should also say that there are some exotic theories that predict such things could be seen. And of course, we're looking. We have the detectors, we might as well look. Okay. Another source would be spinning neutron stars. I talked about pulsars earlier, but we don't have to have a pulsar. Just any ordinary spinning neutron star can provide gravitational waves as long as there's a little bit of asymmetry in that spin. If, for example, it has a mountain, in this case, a mountain means something that's a millimeter high. After all, we're talking about that teaspoonful of billion-ton material. Or if the neutron star is wobbling a little bit. If it's been knocked a little bit off of axis and is precessing around like a child's top, that could also create the kind of asymmetry that we need. Here's a picture in the optical from the Hubble Space Telescope and in the X-ray from the Chandra Telescope. These are both satellite telescopes, showing the Crab pulsar. I talked about that a little bit earlier. This pulsar rotates at a frequency of 29.8 hertz, which means the gravitational wave frequency is twice that at 59.6 hertz. So let me play for you what the Crab pulsar would sound like if we could detect it in gravitational waves. Sounds like a stereo, a bad stereo. And that actually presents a bit of a technical challenge because any detector you build here on the Earth is going, at least here in the United States, is going to have a 60 hertz electronic noise background, and we do have that problem. So it's unfortunate that the Crab ends up being so close to the 60 hertz line. But still, we can do this. We know the rotational characteristics of the Crab pulsar. We can track it. We can pull the signal out if it's there and if it's strong enough. So looking for this sort of gravitational wave ought to be easy. But now what if you don't know where your pulsar is, where your no-tag neutron star is? We know where about 1,500 of them are, but there may be plenty of others out there in our galaxy that we don't know about. So how would we look for those? Well, it turns out that's actually quite difficult to do. It's the hardest search that we do. You would naively expect a single spike in our spectrum, a pure tone like I played for you earlier in the lecture. But in practice, the search is quite difficult for two reasons. One is that the strength of these waves is very, very low. It's of order 10 to the minus 24 or lower, and our sensitivities are of order 10 to the minus 21. That means we have to integrate for very long periods of time to have any chance of seeing these things. And unfortunately, because the Earth is rotating on its spin axis and going around the Sun, the apparent frequency with which we see it will change. That's called a Doppler effect, and I'll talk more about that next week. Bottom line is it's a very hard thing to do, but that's something that our group here at Michigan is working very hard on. We're trying to find these sorts of pulsars, or rotating neutron stars, in gravitational wave data. And I'll say more next week. Okay, let me close by stepping back for a moment and asking, why are we looking for gravitational radiation? Well, for one thing, we're curious. We think it's there, so let's find out about it. We're scientists. Let's explore nature. On a more mundane level, we'd like to test general relativity. We'd like to verify, or not verify, that the radiation is quadrupolar, that it's transverse, that it travels at the speed of light. Is a graviton indeed massless? Also, a little bit more generally, this is a unique probe of strong field gravity in a way that we don't have with our other astronomical measures. We can probe down into collisions of two stars that are whirling around each other at hundreds of hertz. We don't have any other way to do that right now. But I think what's more interesting is that we gain a different view of the universe. The sources of gravitational waves cannot be obscured by dust, as, say, light would be, ordinary light would be. And the sources that we think we might be able to detect in the next few years are some of the most interesting and least understood in the universe. Another way to view it is that we are opening up an entirely new non-electromagnetic spectrum. And we don't know what we're going to find. If you go back and look at 20th century astronomy, we started off in the visible, dominated by the Milky Way, our galaxy. That's where most of the light we see comes from. If you look in the infrared, we're still dominated by our galaxy, but there are some interesting local effects due to our solar system. If we look in microwaves, here we're seeing the fluctuations in the microwave intensity that I already talked about a bit earlier. It's a very different picture. It doesn't look like the galaxy. It looks more isotropic, more uniform, coming at us from all directions on the sky. And that's because this truly is cosmological. It's coming at us from the early times of the universe. There's no reason to pick this part of the sky as being different from that part of the sky in the early universe. If we look in gamma rays at higher frequencies than the optical, we again see our galaxy dominating. However, you also see these little hot spots up here and down here, indicating interesting gamma ray emitters. If we look at what are called gamma ray bursts, GRBs, these are very short-lived phenomena that only happen once per point in the sky, where we have a sudden burst of gamma rays of high energies, and these involve tremendous amounts of energy. These, again, look fairly isotropic. They are not dominated by our galaxy. They're coming at us from very long distances away. And so the question is, what will we see in gravitational waves? Well, we don't know, of course. We don't know yet. My own guess is that we're going to see something that looks a bit like this. We're going to see sources in our own galaxy, for example, neutron stars, rotating neutron stars. But we're probably going to also see some things out here, perhaps these sort of things, gamma ray bursts if we're lucky. And so we'll see a mixture of the two, but we don't know yet. And so the question I want to address next week is what we think we can do to fill in these question marks to tell us what the gravitational wave sky looks like. Thank you.
Saturday Morning Physics is sponsored by the University of Michigan Department of Physics and by gifts from friends of the program. Local broadcast is made possible by Pfizer Incorporated.